13 people. One will be my screen 14. Ravi, are you recording? Okay, thanks. Okay, so I'll share my screen. Start from so that there will be a little bit of delay because I haven't finished the OpenMP and MPI part from yesterday. So we'll come to the SS Labs core maybe 1 hour into after.
Oh, okay. Carry on. I'll be in the call.
Okay. Okay. So yeah, we left off yesterday in a very messy situation because it was too late. I was doing a lot of buggy things. So let's see. I'll just quickly clean up some of these areas and those things. Okay, so what we did was first we refactored our simple 2D thermal solver, FD thermal solver library, and replaced all of the static macros NX system size with the dynamic runtime variable, and we changed the static array to dynamic array. And we saw what the advantages of having a dynamic array is. You can grow larger sizes and so on. Then we tried to use OpenMP to parallelize it. And since it was not working on my laptop, because the two memory channels out of that one doesn't work, we went to Rudra. And in Rudra, we were trying to see how things scale, but we were not getting the correct scaling numbers. So let's start again today with a fresh mind, not tired. And let's see if you can quickly close that. And okay, and in the middle, we also went through a bit of SIMD. We did not benchmark this, but we will do that. Okay. So OpenMP, MPI, SIMD, we'll quickly cover, and then we'll go into actual library writing and how a written library can be used. Okay. So this is the state of our code. Should I just push this once so that everyone has access to it?
Yeah, actually, that'll be good.
Yeah, that'll be nice. Okay, so then I'll just reorganize these copy and all these things a bit. So we'll do tests. Okay, we'll put them in tests only or benchmarks. Okay, benchmarks. So we'll move our copy.cpp to benchmarks because that was anyway a benchmark code. Our simdiad to a benchmarks. And build is not required, so okay. We added it to 9, use dynamic arrays. Okay, so we'll just push this and close this issue. We'll create a new issue where we will do performance scaling and all those things. So we'll push it, and if we go online, we'll see. There is no lag in my voice, right, today? Like
No,
A, B, C, D.
Yeah.
No, I can see it. Nice.
Fine, okay. So we'll go to thermal, and there's one issue open. We'll add a merge request open. We'll do code review, and we'll write a comment that tried to the author tried to do scaling but failed miserably yesterday. Okay. Comment and close. So
It should not be a comment, no, ideally.
it should well see.
It can be, is it? I don't know. I'm just.
No. See, the thing is, technically, see, these are the nice tricks. This is almost the non-coding, or what do you say, management skill tricks that you can pick up on the side. That if the issue is a dynamic arrays, technically your commit or push should not be evaluated for the scaling part. If you want scaling, open a new issue called scaling.
No, okay. Got it. Right.
Okay, so anyway, what happened? It did not. Doesn't seem to have closed this, is it? Or is it closed? No, not close, right? I did a very stupid thing. I just closed the merge request instead of actually doing a merge. Very sorry. Reopen merge request. This is still in draft stage, so we'll mark as ready and we'll do a merge. Okay. So this will now close the issue. So it's closed. The branch is also gone. Only the main branch is here. And it is going into our running pipeline. Pipeline hopefully will pass because we haven't made any change which will break anything, right? But we'll see. Let's see what it does. If it breaks, it breaks. What to do. In the meantime, we'll open a new issue. Today is scaling and library usage. So use OpenMP to scale across threads. Scaling means scale performance. Create a merge request. And so on. Okay. So let's quickly look back at what is happening in pipelines. Did it pass? Did it fail? Oh, both are running. Okay, it compiled. And it's going through the unit tests. Just see quickly. Oh, good. Unit test pass. So it'll pass. So we'll go to our repo, clean it up. We are in branch this. We'll check out domain. Dynamic array thing is done. So create branch minus D9. And then we will git pull for the new branch. So many things. Git checkout 10 would be the new branch. Now we are in 10. So let's get into the benchmark part.
Samir, one quick question. Is it a good thing to practice to delete the branches like this? Because then you have no, I mean, you have closed the issue and stuff, but you have no track of what has happened.
See, if you go to graph.
Oh, it's there here, is it? Okay.
Online, if you git push all your stuff, everything.
Oh, it's
will be
all
recorded.
online. Oh,
Yeah,
so
yeah.
it's all recorded here. Okay.
Yeah. Means that's the thing. So basically, the idea is if your laptop burns in a house fire, okay, your data still should be preserved.
Right. Got it.
That's why you
cool.
git.
Yeah.
What
So-
an example.
I'm saying extreme cases. Otherwise, if your laptop is still there and you keep building locally here, it's technically not any problem. It's just,
Right.
or suppose you die. Okay. Then,
It doesn't even matter.
okay. No, basically the thing is,
Yeah.
you can always revert back to any
Yeah.
page 2-3 days ago also and so on. Like
Yeah.
any other previous comment, you can revert back to. So basically, okay, just to revert back to a comment. So if you do git log, you'll see all the list of comments that you have made. Or if you want, you can do a git log pretty one line to see what is the thing.
One line.
One. Oh, one. Okay. So you can see all the comments. So suppose I want to go back to the stage where I was fixing the CI script. Huh? You can pick up this huge number or just pick up a 7-8 digits from there. Okay.
Oh, okay. So the branch is just okay.
Yeah. It's just for you to have a separate development in case you don't want to mess with the main branch.
Cool. So the logs are always anyways there.
Yeah, logs are always there. That's why it's very lie to lie about development on Git. If you say, yeah, sir, I did it 2 days ago only, and there's a very good comment.
Right. Yeah.
Okay, so you can check out, and then now you will see you are in. Okay, anyway. No, there is no benchmark folder here. Yeah, that's why it's showing. So this was the old state. And now you can check out the main one only. You can check out head. Head is always the latest one. Oh, sorry. Head is right now this one only. You can check out to the 10 branch. Okay.
Hey, Matt, can you give us access to this?
I think it is open, public.
Oh.
You don't have access, is it?
One second.
Yeah, I think we have access.
Yeah. It's public, I think. You can see this, right? All this.
Yes, yes, yeah.
If you can see this, then you can go in like this and this. And you can go in here.
Oh yeah. Okay.
Okay. So I still forgot to delete the package.sh. Okay, let's do that here itself. So git branch, and see, now that you have like checked out and gone away from that intermediate temporary branch, it is not visible. So it was technically not a branch, it was just you had checked out that commit. So you can go back and forth between commit if you want to really start working. So suppose I decide the last 1 day's work has been very bad. I really want to, like, I can't erase it because it's on Git, but the code structure should not reflect that 1 days of work. Then you can go down the commit history, and suppose you check out from here, this commit, and start working, it will branch, and then you check out this commit, then branch out from here, do your development from here, and then merge it back to main. Then that is also possible. So basically all these things will be overwritten in the final code repo that you have. History wise, it won't be overwritten. It's very hard to rewrite Git history, especially if you don't have maintainer access. Yeah, so let's quickly start doing the benchmark stuff, because my aim is to finish benchmarking by 12:30 and then go to SSLab score by in the afternoon. Now, there was no afternoon and a half schedule for Thursday today, but as you can see, if you want to stay back, we can do it. It's not a compulsory thing because it was not in the schedule. Okay, so remove package is not recorded. Benchmarks. We were looking at this simple example, which is copy. So we had this very explicitly written parallel region where we have OMP parallel. We are spawning 2 threads here, and we are asking one of the threads to do the job here and one of the threads to do the job here. And we were trying to see if it scales or not. On my laptop, it's a bit difficult to scale because even none of the things give good scaling. Actually, in many of your laptops, you'll find it's a bit difficult to scale memory bandwidth limited codes if you have only 2 memory channels. So what we'll do is we'll copy this to Rudra and do stuff there. So, let's see. I'll copy it here itself into desk. We'll go into desk. So we had all these things from yesterday. To delete all those things. We'll start afresh. Let me keep that stream because we might come to stream for a reference benchmark. So as we were saying yesterday, stream is basically like this copy example where you're doing a bx equals ax. Apart from that, it also has other kernels like, so let's see. Standard benchmark codes that people write for simple memory bandwidth limited operations look like this. One is this copy, which is basically ax equals bx. There is something called scale. Scaling means you're just multiplying your variable with a constant number. So ax equals c into bx. Okay. Or some people call it k. Third is another kernel is add, which is ax equals bx plus another array element cx. So you're taking 2 numbers and adding them. We were trying to do a SIMD on that add operation. And there's things called triad, or it's also called PAXY, which basically is like a fused multiply and add. So AX equals K into BX plus CX. Okay. These are standard kernels that people evaluate to evaluate standard speeds on a hardware. Okay, so stream basically does this only. Like instead of just doing copy only, it also measures the speed of like it has other consecutive code where it goes over n samples of these loops for the other 3 also. So anyway, we will this just to know, like if you have any doubts on the performance of your code, always download stream. I showed you that like stream is available at stream.c would be this thing. Stream.c, you can search for it and you'll see this guy Virginia person McAlpin, and you can copy this code and run it. And then you can see how much it is performing. As you're discussing, you know the hardware limit, you know how to calculate the hardware memory bandwidth for multiple memory channels or for one memory channel. Just run the stream on multiple threads or one thread and so on, and see how much you're getting compared to the hardware. Usually for Intel AMD processors, depending on the motherboard and all these combinations, the maximum performance you'll get is around 80 to 85% of the hardware limit. So usually for theoretical estimates, you consider stream's performance itself, because if stream cannot reach the maximum, cross that maximum threshold, your code also most probably won't. It won't. Okay. Means stream is a very simple code. Like this copy is a very simple code. If this itself doesn't perform well, then your complicated codes will definitely not perform well. Okay. So we will again run stream later on. So now let's just quickly try to run this case once. So what we were doing yesterday was GCC. Okay, let's do GCC first. So we will do I can't do it on my desktop. Just drop into the interactive shell. So Q sub. This is the interactive shell. Okay. Okay, I'm in a node now. If people, you want to know where the interactive shell is, just go to the systems repo, and it will be there in the section on Rudra. Here. If you search for interactive, it will tell you what the command is here. So what we'll do is we'll module load GCC. The multiple GCCs, so you can use anyone you want, 10 latest one will use. So with GCC, we will do a -03, that is important, and it's OpenMP, so F OpenMP. And then copy.cpp. So copy, just executable. So we're compiling. Once you have compiled, if you try to just do export OMP, oh no, we don't need to do this actually, because it's already put here, this thing. The only thing is, as we saw yesterday when we were doing OMP display environment, which tells us what the settings are of OMP. It was showing that sometimes it can take up some small variations in the number of threads as well. So it is always good to keep a control over your number of threads from an environment variable OMP num threads. So we'll create an array of suppose 1 billion elements. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, 10 iterations. Let's see how long it takes. So this shows you all the OpenMP variable settings. Here it says num threads is 16, whereas it technically should have been 2. But internally it might be using 2. You never know. That is why it's a bit of a bad habit to hard code the number of threads that you're using inside the code itself. It's all. This is best not done. Always try to control your number of threads that you're launching from outside using this export OMP num threads equals whatever your number of threads is. So okay, let's see. It gave me a total elapsed time of 6.8. Let's go back to our theoretical estimates section. We'll just ignore yesterday's theoretical estimates and do it afresh. Always start with a fresh brain in the morning.
So maybe this on Rudra, when you're compiling now, you don't have a submit script. So is that okay, like for small things?
Yes. So basically, yeah. Okay. So the thing is, as you saw me drop down into the login node interactively.
Oh, okay.
So this is like you basically got your own node to play around with. Like,
so you don't need.
You can
Okay.
You can do whatever you want. Submit script is basically you want to schedule the job.
Okay.
Okay. Like and if it's a multi-node job, because if you log into a machine like this interactively, you'll be able to use only that node, unless you do a lot of SSH connectivity for MPI and all this by yourself.
So this node is not used by other jobs, you're saying?
No. So basically, if you now go to the queue, you will see you will see that it says, I am using something here.
Yes.
Okay, one node with stdin test queue.
Mm.
So
Okay.
it is blocked for at least 1 hour. You
Okay.
have blocked it for only 10 minutes. Because in that sample script, I blocked it for only 10 minutes.
Ah,
So
10 minutes. Okay.
you can change it. Maximum test queue runtime is, I think, 4 hours. Okay. Right.
And 2 nodes, no? You've included now.
Maximum 2 nodes, but interactively, there is no point of 2 nodes. It will be, you'll be logged into 1 node only. Yeah.
One node only. Okay.
Yeah.
So with that one node, you can do testing and stuff. You can just log in.
Quickly.
Okay.
Means otherwise, keeping on submitting Q sub for small things
Correct.
becomes irritating.
Exactly. Nice. Okay.
Okay. Yeah. So we got a 6.8 elapsed time for 10 iterations with a 1 billion element array. So we'll do a theoretical estimate quickly. Theoretical estimate for hop. So let's see. We got our number. By the way, if we also okay, number of threads is 2. So number of assuming number of channels is also 2 being used. Let's call it number of channels. Only number of channels is 2, and your machine has, so RAM MTS is 3200 megahertz per Rutla, and you're doing two channels. So your 2-channel memory bandwidth will be 2 channels into 2.2 giga MTS, or which means GTS, not giga MTS, GTS into 8 bytes. So which is 16 into 3.2, which will give you around, see, 16 into 3.2 is 51.2 Gbps. This is your 2-channel memory bandwidth. And now, if you look at this one, so this is hardware. And if you check this timing, it is, you took a copy from test. It is $1 billion elements I've used, and iterations. So basically, the amount of data that I'm transferring is, there is 1 billion reads for each element into 10 iterations, and 1 billion writes, because AX equals BX means BX will be read from the RAM and AX will be written back to RAM. Writes into 10. Okay. So basically, data traffic would be total of 10 billion into, so 2 billion into 10 into 8 bytes, which is 160 GB. Okay, that's the amount of traffic we are generating. And wall time taken is 6.8 seconds. 6.8 seconds. So obtained bandwidth will be this divided by 6.8. 160 divided by 6.8, which is 23.5 Gbps. So which is around half of what we were expecting. Okay. Now, if you find yourself in this situation that you're not reaching the best possible, like the limits of physics itself, the limits of hardware itself, just introduce a step in between. Stream bandwidth test. Because if stream bandwidth also doesn't reach this level, that means the hardware is not, like, no other code can actually. So we'll do the stream bandwidth check also with 2 channels. So number of threads we'll use for stream is 2. Size we'll use the same size that we are using. So that will be 10 billion. So stream array size so this is the variable they use for deciding the size of each array as a compiled parameter, is 1 billion elements. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And so this will be a thing, and D, I think in stream, this array size and number of steps is controlled by the variable called, see, stream array size is this. By default, they take, I think, 10 million, will go to 1 billion. N times. N times is basically the number of times iterations happen, or n samples. So n times will be 10. And then we'll find out what is the obtained bandwidth. I will give you the time and the bandwidth also. We'll reiterate the bandwidth. So let's compile stream like this. G++ minus O3, same thing that we used. Okay, by the way, stream is a C code, so you can use GCC. So stream.c and stream. Okay. Now, whatever environment we have, export displays there. Now, stream doesn't have, if you look at the stream code, it won't have, just one minute, pings happening. Mute my phone. Yeah. If you look at the stream code, it doesn't, in the Hashpragma OMP parallels, it doesn't use a hard-coded number of threads. So you have to set it outside. Okay. So you set your export OMP num threads outside 2, and then you will run it. It will tell you how much bandwidth you got. So you have, why did it? Oh, sorry, I'm very sorry. I forgot to compile with the stream array size. So we were supposed to 1, 2, 3, 1, 2, 3, 1, 2, 3. And minus d n times is 10. Okay, something happened here. Relocation truncated to fit this thing, blah, blah, blah. Whenever you see something like this, okay, you'll also see something like additional relocation overflows. So basically, this means there is some overflow happening. What is the overflow that is happening? One is that you're trying to allocate 1 billion elements. And if something overflows, see, 1 billion element would be 1 billion into 8 bytes, so 8 GB. And there are 3 such arrays as you saw inside stream. So 3 into 8, which will be 24 GB. 24 GB is not a problem because your RAM size itself is, I think, how much? 3 is 479 GB. So that means it's not a RAM issue. The only other issue where there will be a reallocation, like compile time reallocation error like this, relocation error because of overflow like this is static arrays. So if you actually open up stream, as we learned yesterday, that if you do a static array, you can only fill in a particular size, which depends on the stack size of your program. As you can see, the ABC arrays that stream uses is a static array, are static arrays. So the stream array size number cannot be larger than some million or something. But there are compiler flags which will allow you to control the size of the stack overall. Not exactly, but there are 3 categories: small, medium, large stacks. Okay. But you can, let me check if GCC allows that first. So usually by default, it is small. It will throw this error. If you go to medium, it goes through. Okay. MC model, this parameter basically means the machine model, where it tells the program how much, or the compiled binary, how much memory can be allocated for stack. You can't exactly allocate like 13 MB or 54 MB and so on. You can just give categories, small, medium, and there is something called large also. Okay. So if you're trying to use static arrays for everything, you really have no other choice. Usually that is not, in practical cases, dynamic arrays will be able to handle whatever use case you have of using a billion element static array. But just in case you want to use something like that, a huge static array, you can try Mac model large. This doesn't mean it will allow you to allocate the entire static array on the entire RAM. This also has a limit. Okay, I think it is something, I don't know. We have to see, it depends on the compiler and all those things. So, okay, fine. So we'll allow it to allocate this much, 1 GB of 1 billion elements in static. So if we now run it, this will take a bit of time. We compiled it, right? Yeah, compiled. So now we have export OMP num threads 2. and we'll run stream. So you can see it says number of threads using is 2. And it also tells you what your clock, what stream's internal clock resolution is 1 microsecond. It says it will take 0.4 microseconds per time. Oh, each test, okay. So be 40 seconds, yeah. Okay, so as you can see, you're getting 31,000 Mbps, which basically means 31 Gbps or 27 or 43. So copy type of kernels are supposed to get 43, scale type of kernels are supposed to get 27, and add is supposed to get 31, and so on. Okay, so we will do this.
Why is getting this less?
We'll see, we'll come to it step by step. So 51 was the theoretical limit. Getting 43 is not a theoretical hardware limit. Getting 43 is not that bad. The question is, why is scale like this, right? That is your question. We'll come to it. That actually depends on the optimizations you use and also the compiler and hardware and so on. So I will come to it. For Intel, it's different. For AMD, it's different. And yeah. The obtained bandwidth for scale. Okay, so one important thing that we need to notice, Rudra estimate for copy, we will use stream bandwidth with GCC, 10 point. Just keep a note of the compiler versions you're using, because that also changes, because some compilers will not have certain optimization flags, and then you won't be able to optimize for particular cases. So always remember to note down the compiler versions you're using. And obviously the hardware, so in this case it is. So bandwidth obtained, we'll just copy paste this. Okay, so now this is the hardware estimate. So if you can see, the copy took for stream 43, but we got 23. So why did it happen like this? So the first thing we can do is, we can try to get as close to stream as possible. Means try to mimic the code as much as possible. That is one way of tackling optimizing codes. If you have any doubt, just try to open stream, study the code. Actually, it's a very good idea to always study what stream does. Stream is not a big code, it's how many? Just 500 lines. There is comments also. If you go up, it's like this big comments. So if you just ignore that, it's 500 lines or something. Or actually 400 lines only. That too, the main portion is just this initialization over stream, and then you're running this is the copy loop, Cj equals Aj. This is the scale loop, Bj equals scalar into Cj, and then where is that? Add loop, which is Cj equals Aj plus Bj, and this is the triad loop. Okay, so it's not that difficult. Remaining portions are just checks and timings and all those things. Okay, so the one thing we can see from stream is, okay, one thing is they're using static array, but instead of rewriting, going back to static arrays and all, let's keep our dynamic arrays. That won't change performance much, because both reside on the RAM, and if it's too large, it anyway won't fit in the cache, so it will stay in the RAM, and the be it static, be it dynamic, it will keep going back and forth. Like the data has to be fetched from RAM only, not from cache. So that is fine. The other thing that they're doing is they're using #OMP parallel 4 and controlling the number of threads from outside. So maybe we should try that once. Let's see if that improves our stuff. So we'll go to our copy. And as you can see in this code, there are two things we have done. One is you have explicitly used, first of all, you have just split the region into this thing. And then we have used OMP num threads 2 explicitly. The third thing, and the very important thing that we were discussing yesterday about the actual practice of allocation inside the processor OS, is if you don't parallelize the initialization also, then this initial or allocation of memory will happen in one weird RAM stick, and then the other threads, if they're on different cores, they will have to travel a long distance to get this. So what we'll do is, first, instead of doing any changes, we'll go back to what we were trying to do yesterday, and we'll just try to do the initialization in the same way that we are going to actually use the data. So after doing that, we'll compile again this stream. So we'll leave out stream, we'll compile our own code. That code. We'll run it. Here we ran it with that big number. Here. So let's see.
You compiled stream.
Oh, sorry. I'll just change the. I was wondering why is it okay. Copy. The CPP, so we'll use G++. Okay, so it's 4.3 now. So you can just by putting a hash pragma parallel over the initialization, we brought it down from 6.8 to 4.3. So now you can see how much effect the distance business has over. So we're here. So how much the distance business has over your bandwidth efficiency. Like if the data is allocated here and the thread is running here, it does make. Now we don't know where exactly the thread was allocated, but clearly that was the case because just putting a parallel over the initialization reduced the, and we are timing not the initialization. So it's not like that the initialization timing reduced. We are starting the timer with the copy case only. So that's fine. So we'll say that we'll update. Great news. GCC. So this was a point. Then we'll keep replying in the same thread that great success. We were able to initialize parallelized in the same way data use is parallelized. Okay. So we will .3, huh? Yeah, 4.3. Means it gives me a bandwidth of 160 divided by 4.3, which is 37. It's good, not the greatest, good. Okay. So how much do we have to go to? 43. Yeah. Usually for one channel, two channel cases, we don't nitpick that much, but okay, fine. Let's do one thing. Let's now make other changes, which might be useful for us, maybe. So as we learned yesterday, that if we try to spawn more threads, again, hard coding is not the best way to do things. So if we have to remove this, we can still use this. So let's do that. First, remove this and just use export. So we are doing very snail-paced step by step, just to show that what each of these options do and don't. It is very clear. What we will still use we will still do an export of two threads. So it's already there, but okay. And then we'll time. Let's see. One problem you might, okay, so it doesn't make as much of a difference, but it's a good practice to control outside because then at runtime you can change the number of threads as you wish. And so at runtime means, I mean, before starting the run. One thing that is a bit of a problem is this. Okay, let's leave that for now. Okay, let's see what all changes we can make. So one is this OMP parallel business. Achha, by the way, we initialized that, but we did it in a very weird way, in the sense that we tried to initialize this thing in both the threads. Ideally, we should have followed the exact pattern, right? Like this. If this is the case, then both the threads will be trying to initialize the same array, and then you'll have a lot of confusion. Maybe accidentally they allocated the right way, but you should time it once more just to be thorough. So 1.5 and because these bugs will give you some 10x improvement and will really get your hopes high. Then when actual code audit happens, you'll see that it's a bug. Actually, it can get 10x high. I think full emotional crash will happen. Okay, it's even better. Wow. So that means some of this rewriting was basically trying to push the data for that portion of the thread to other RAM, so the other RAM as well. So now we are at 3.7. It's great. So technically, initializing it properly would have given 3.7. So let's just note down this as 3.7, 5, 6 we will put. We're getting such good speeds, we're ready to take the worst case, round offs. 3.76 is 42.55. I think we can call it a day here, like a 43 and 42.55. Fine, okay. Let's give Stream the honor it deserves by getting 0.5 GBps extra. Okay. So we have seen that our simple copy operation reaches the industry standard benchmark that is currently there for copy. Okay, on this processor. This is for AMD Rome. You can AMD Rome is not currently the latest processor from AMD. AMD Milan is. It has the same architecture. You'll get almost the same bandwidth. So let's, as you were seeing yesterday, right? That AMD 7746 or something. It's the new. What were we checking yesterday? AMD 7763. Yeah, this is Milan. This is the newest processor, and you can see the specs here. So same thing. 3.2 GTS, DDR4, 8 channels per processor. So, and Intel's best processor currently is 8380. Yeah, because Ice Lake. And similar things you'll get there with a 75% lower bandwidth in Stream itself than the theoretical bandwidth that you'll calculate from here. If you want, we can do a test on these machines because we have access to them, but let's not waste time. Otherwise, it'll be good. Optional class, we can do it. We can run on both Milan and Ice Lake and see how it works. Okay. So we'll now go back to OpenMP and multi-threading. Like this is only 2 threads. Now we'll use as many threads as we want, and we'll try to see what is the maximum bandwidth or speed you can get on any memory bandwidth limited code on these systems. By the way, I realized I've been using this memory bandwidth limited word quite often. Is everyone familiar with what it means? So basically it means this. See, right now, look at the main operations you're doing most of the time. AX equals BX. Huh? If instead my algorithm was, I will do AX plus 1.54 into 3.6, and we'll take a cosine of that and do an exponential of this thing. You will basically be doing not only a memory transfer of B from the RAM and then writing A back to RAM, you'll also be doing a lot of mathematical operations or arithmetic and algebraic operations. So these algebraic operations, if you look at the standard C++ implementation of, not here, the C++, in the GCC library, for example, if you look at the, so it's called what? libstd, C++. If you look at the source code, they also use Doctogen only. To document their code. Okay, so you can look at GCC's source code of the compiler itself. And this is a very good place to learn programming actually, because you will see how the industry writes C++ code. Okay. So if you look at, the problem is they don't have search. They haven't enabled the search option, so it's very, very bad. But if you basically go down this class list and try to see where they might have a cos or sine or something like that. It's really cos only, no? Trigonometry might be. Square root, no. Cos, no. Okay, fine. May I have to see exactly where it is. You will see that they most probably have used something called Paddy approximates in implementing it. So basically, or if you can think of it like this, think that there will be if-else condition if cos, the argument of cos is less than something, they use a Taylor series expansion, or if it is more than something, they will try to scale it back and make it less than some reference value, or they will use Paddy approximates. Okay, or exponential is also like that. Most of it is Taylor series to a very high degree of accuracy. Okay. So this is how it's implemented. So basically, if you remember Taylor series, that is also a lot of plus, plus, plus into square, square, cube, and all those things, right? So in the end, it's usually boils down to a huge number of additions, subtraction, multiplications, divisions. Now, if you look at the instructions in any of Intel's instruction set, like for example, Intel add cycles, as we were looking at yesterday, addition, multiplication, even subtraction takes only one cycle. So as I was showing you, like if you go to instruction tables of Agner-Fogg, you will find that addition and multiplication take only one cycle each. So it's very fast. At one shot, it will finish off the operation. But division usually takes 10 to 20 operations depending on the implementation and so on. Okay. So if you look at div or something, a lot of div. So as you can see here, it will take some 47 to 24 operations. Cycles, sorry. So ops is this much, latency is this much. There's a difference between the two, but just forget about it. Just think like the higher the number here, the slower it is. Okay. So divisions are usually very bad. Multiplications, fast enough, 3, 2. Additions, 1 cycle. Subtraction, 1 cycle. So if you can replace your divisions and so exponential, then cos, sine, all these complicated algebraic or trigonometric functions that you use from the library, those are actually very heavy. Like exponential might have multiple divisions inside it. So it can go up to 200 operations itself or cycles itself. So it is best if you want to really optimize or minimize your compute part, then you can try to replace this with approximate plus minus based formulas. That's why, for example, if there's a famous example of how it was done. 1 by square root is a very costly operation because square root also has a lot of like internal floating point operations, arithmetic operations going on. And 1 by square root of something, or the inverse square root problem of x, is actually a very costly operation. Now, this 1 by square root of x used to keep coming within ray tracing in video games in the 1980s. A 1980s video game, if you remember, is very original. It's called Doom. It used to look. Oh, quick. Yeah, right. Today morning I read something about Doom. That's why it was. Okay, it used to look something like this. Surprisingly, when players, so basically, players used to get very low quality graphics like that Mario 64-bit thing because anyway, it was 2D. 3D games also, it was very choppy. And like if you have played Wolfenstein and things like that, it used to be very choppy. Suddenly, when people download this version of Quake and start playing it, they saw it's very smooth and they were surprised. How are they doing it? Okay. So then people found out that developers had been too smart, almost like mathematicians, like proper trained mathematicians level smart. Although they were just software developers. So inverse square root, if you go to the Wikipedia page of fast inverse square root, you will see the portion of the source code that they had there. They said the square root of the number, instead of using mathematical plus minus addition division, they replaced it with a bitwise shift operation. And this is what they commented about. Okay. So it became from a 200
What is
cycle.
that comment? I mean, they have only said what the fuck.
Yeah. Because this was such a genius level stuff. Like they were also like amazed by their own genius. So basically from 300 operations or something, they brought it down to 1 operation or 2 operations. Okay, so it became 150 times faster. They're ray tracing.
Crazy.
What is this, man? I don't even okay, I think you understand this, but what?
No, so basically, if you go to this lookup table of how 1 by square root behaves, you will see that this one, sorry, not this one. So there is in Wikipedia only. If you just go to the links, it explains how it is so.
Okay.
Like why it should be so.
Okay,
Because
okay.
It's basically a heuristic observation-based formula that they got,
Okay,
which is valid for most of the practical cases.
Mhm.
It's like Newton's laws or special relativity and so on. It's valid for most practical cases.
Most practical. Right. Nice and fast, very fast.
Very fast, yeah. So you can kill your enemies like like this instead of
Or
shooting and
beat
then waiting to see if the die did the die.
But it's not for double, right? It's only for float.
It's
I mean,
only
it
for
has,
float,
it
yeah,
has precision issues, right?
Yeah.
Oh, okay.
Yeah. So for graphics and all, you don't use structured grid, you use STLs, you don't use floats, you use double, and nowadays the people are even using that half float kind of thing, 16-bit. So yeah, graphics basically as long as you can fool the human eye, it's fine. In scientific computing, you have to go for actual quantitative accuracy. That's why I use float, double. But anyway, okay, we'll come to it. So fine, we see that, okay, we were discussing what is memory bandwidth limited and for instance, what other limitations can be there possibly. So when you have a code which has a lot of these kind of arithmetic operations or so-called floating point operations, floating point basically means there's a point which keeps floating between a series of numbers to make it a decimal number. So which means it's a real number. So when people say floating point, it means roughly it means a real number. If you talk to actual computer scientists, they will like commit suicide if they hear this sort of distorted definition, but okay, fine. Real number operations, if you see, you have quite a few. You can actually calculate how long it will take for the real number operations themselves. How do you do that? You again go to one of these pages where they brag about their processor frequency, base frequency. And so essentially what this means is at this clock cycle speed, there are instructions being processed. So how many floating point operations do you have? So basically, how many addition operation calls are you calling? How many subtraction operations are you using? If you make a list of those, suppose in this case, so this is where it becomes a bit tricky. Where am I? In this case, suppose instead of all this cost sign, because it's a bit opaque, you have to actually see the implementation of these things to figure out how many instructions they're using. Suppose I just say, I am doing this. I am adding this number and multiplying with 3.6. Both these are floating point, AX and BX is all floating point. So I have one addition and one multiplication. Those are the floating point operations, my arithmetic operations I'm using. That means I have two instructions to process. Assuming that these instructions take one cycle each, which is not the case as you saw, it will take multiple cycles maybe. And from the table you can find, assuming for simplicity of calculation, how much time should one such statement take? So you have here 2.3 clock cycles, which means it can process that many operations simultaneously. If you have used SIMD as well, then it will be doing 4 such operations or 8 such operations at one shot, depending on the depending on the vector width of your SIMD, what your machine supports. So for these cases, the server-specific models, which is Ice Lake and so on, it will support AVX 512, which is like 512-bit. And I think 512 comes to around 64 bits, 64 bytes, sorry. So 64 bytes. So it will be able to process 64 bytes per cycle. So how many, or 64 bytes basically means how many doubles do you have? Or 512 bits, 8 doubles, 8 doubles. So basically it will be able to take 8 doubles per second. And then there is extra number. Wait, I'll just quickly refer to the formula I usually have. So there's a number of 32 which comes. Ravi knows this calculation very well. You can ask him exactly where it comes from. Sorry. So let's see. What is the compute speed? There's a number of processors or sockets. OC is the operations per cycle, and NCR is the number of cores, obviously, because we are doing this for each core, there will be multiple cores in your processor. And then FP is the frequency, which is the clock cycles. So for Ice Lake or any of these, you will see that the operations per cycle is 32, and this is 16. The reason for this is basically that AMD machines currently support AVX2 only, like your laptops. It supports AVX2 only, still it is that good. Okay. And Intel processors currently, server grade processors, the new generation ones, Skylake, Cascade Lake, Ice Lake, they support AVX 512, which is twice, it fits twice the more data in one register than AVX2. That's why the operations per cycle is double of that. So basically 32 operations per cycle, if you take and multiply with your 2.3 gigahertz. Let's do this calculation. So 32 operations. Let's do it for AMD only. Then we can actually figure out quickly how. So if you go to AMD, our model is 7742. So as you can see, it goes up to 3.4, but this is only for single core cases. When you're using all cores parallelly, it will reduce, and including if you use AVX2 on all cores, it will reduce further to the base clock itself. So whenever you're calculating the flops of your machine or flops of your entire cluster, okay, that is the standard for all these competitions, like who has the largest cluster and so on. So always use the base frequency, because when you're actually doing real life practical HPC simulations, you will hit only the base frequency. Only when all the cores are off, only one core is on, Intel can boost up one core to a higher turbo frequency. Otherwise, it will melt. If it does this frequency on all the cores, it will melt, and melt the whole data center also. So 2.25 is the base frequency into 16 operations per cycle into number of cores. As you can see, number of cores per processor is 64. And we have 2 processors per socket, so it will be into 2. So 4,608 gigaflops or operations you can do per second. Okay. Or billion operations you can do, 4.6 billion operations you can do per second on this Rudra node. These are double counts which we are calculating. If you want float, it will be, you can pack in twice the number in that. So for float, if you're doing floating point, like float 32-bit floating point calculations, you'll be doing 9.2 billion operations per second, or 9.2 billion additions, subtractions, and so on, like total of that per second. So this is the funda of flops. Now the question is, what is the wall time taken by this memory transfer, data transfer from RAM to cache, versus what is the time taken by your floating point operations? Because if you have, suppose, 1 billion operations in your whole algorithm, and your processor supports this many flops, then you can find out how much wall time it will take. So your number of operations divided by flops will give you the wall time taken for your compute portion. So wall time taken by the compute portion, is it less than or more than the wall time taken by the memory bandwidth transfer portion, okay? Memory bandwidth based data transfer portion. If the memory bandwidth based data transfer portion is much higher than the compute portion, which it is in this case, because as you can see, there are very few operations, like 2 operations per element means basically 2 billion operations for a 1 billion size array. And as you can see from this node, per core, it will go up to how much? You can calculate all those things. So you will see, if you actually calculate the wall times, should we do it quickly, or is it okay? If you actually calculate the wall time, you will see that the wall time taken for transferring, the theoretical wall time taken for transferring this data, which is here, which we've found out here, almost this one. This is not the theoretical wall time. The theoretical wall time will be based on the hardware bandwidth. But if you do that, you will see that the wall time for data transfer will be much more than the wall time taken for just doing this compute portion, which basically means that even if you try to add more flops and more core counts to your machine, it won't speed up your problem, because the data transfer portion is limited not by core count, it is limited by the number of memory channels you have, taking your data from the RAM to the processor. Okay, so if your code mostly spends its wall time in the data transfer portion, to speed it up, the only way is to either put in higher MTS RAM or higher clock cycles, clock speed RAMs. So instead of 3200 MTS, you should put 4000 and so on, but that is not available in DDR4 as of now. You have to go to DDR5 or HBM and so on. Or what you can do is you can try to increase the number of memory channels in your thing, but that is also limited by the processor itself. So you have to change your processor then. Okay. But if you find that your data, you are picking up only one element from a small array, and then you are doing thousands of operations juggling around with the same number. Okay, the best example for that is basically cryptography, where you generate, how do you generate passwords or break passwords and things like that. So usually you will see, okay, since we're going into that, we'll quickly look at what a compute bound kernel looks like. So right now I showed you copy is a memory bandwidth bound kernel or function. A compute bound kernel is basically crypto. I'll do a simple hash function. Huh? A simple hash function basically does this. So suppose I give you a password, huh? std string password is ABC B123. Essentially, how Google are this will be a 5-minute segue, but it's a very interesting segue. So just I quickly go through this. What Google or Facebook or any of these websites you log into, they do is they will not just take your password and store it plain text on your server. Okay, that is against all kinds of different security policies, because the moment some this black hat guy gets access to your storage server, their storage server, they will be able to read everyone's password and it's lost. Facebook will be shamed all over the world and so on. So what they do is they will take your password and run it through a jumbler, okay, or what is called a hash function. So what does a hash function look like? It will basically take your password and this will take out. So this is my hash function. I'll show you what the internals of a hash function look like. It will take your password, jumble it very badly, and output it as a jumbled thing. This jumbled thing is called a hash. Okay. So if you have seen online MD5 hash and things like this, which you use to verify the integrity of your downloads, this is basically that. So it can be a MD5 hash function, hash MD5, or it can be a SHA-2, SHA-3, or AES, which is a military grade encryption thing, or something like that. So basically, not all hash functions are used for security purposes. There are some cryptography grade hash functions. There are some file download verification grade hash functions. So MD5 is very simple. MD5 is already cracked, so it can't be used for security purposes. Just for file verification, it's okay. So there's a hash function like this. Its hash will look something like a jumbled thing. So it will look like something. So essentially what they're doing is there is a huge different hash functions working in a different way. So they will take the bitwise representation of your big string. So suppose the string itself was big, huh? Like huge. I used a very big, or it was an essay, suppose. This is my best machine or something like that, blah, blah, blah. Some essay was there. Hash functions will usually reduce it down to a very small signature. Usually it is 256-bit long or 128-bit long or 512-bit long, depending on how strong you want the encryption to be. So the hash functions will convert this entire thing into the bitwise representation. So each character usually takes, I think, how much? 8 bits, each letter, as a car variable. And then if you use the bitwise representation of this huge array, how do you do that actually? How do you get the bitwise representation of a string like this? Essentially what you do is you alloc, suppose a number. Well, you can print, okay, let's do it this way. You can go to a size t or uint 64 type, 64-bit unsigned integer type array. So I'll call this the bit password, okay, bitwise representation of the password. And malloc, or sorry, not malloc, no, malloc also, new uint 64t. By the way, this uint 64t just you can include by using C, what is it? C int types or cstd int types, something it's called. C int types, yeah. So basically it gives you a nice control over whether it's actually 64 or 32, because in some old machines, int might be 16 bits and long might be 32 bits and so on. So your code might not run properly if compiled there, if compiled for a different machine and so on. Okay, so you will basically allocate how much the password length is itself, so password size. By the way, this is not, if you want to do a one-to-one transfer, this would not be the exact size you should basically divide by the size of one character. So size of one character var and multiply by the size of one int. So something. So let's just assume it's some size. So you can figure out later what it is. So 1000, fine. We put a lot of things. Okay. Now, instead of passing the actual password, what they do is they pass a bitwise representation. And from this, the standard way of doing it is, usually they use 32, you know. It's okay, I'll use a very simple one which uses 32 instead of 64. Because 64 ones are a bit complicated to write. A simple 3D hash function will take in a representation like this. Let's assume for now there is only one size, like this. And we'll reduce it to one size like that. So let's say it's AB. Because otherwise I have to loop over the thing and it will make the code a bit ugly. Suppose this was my password. And this is my thing. Oh, I did not transfer it. You do a mem copy. So mem CPI. If it is just one, then leave this allocation business. We'll just use this bitwise representation of your password. Mem copy. So you're basically copying bitwise from your string password. This is the string data type exposes its underlying data structure using data. From that to bit password. If we give the pointer to this, so it will be this. An std mem copy, I think, is available in C string. Now you will run your hash function over this bit password thing. So you will run it over uint32. I'll send the input and it will produce the output. Output usually is just a mangled up form, which looks like this. Input into some constant C1 plus some constant C2, the whole thing modulo 32 bits. 32 bits, so basically 2 to the power 32. This is a very simple hash function. It's called a linear congruential generator. Okay, and I think the particular values of C1, C2 are also known because depending on the values of C1, C2, it will determine how jumbled up the output looks like. So if your input was suppose 1, the output should not be 2 or 3 or something, which is very close by. It should be anywhere between the 2 to the power 32 bit range, like space range. 2 to the power 32, unsigned integer can store, I think, up to 2 billion, like size of 2 billion, like the value of 2 billion, up to that it can store from 0 to 2 billion. So if I input 3, the jumbled up output can be some 73,292 or something like that. Okay. The more the jumbling, the better the hash function is, because then the evil people won't be able to back calculate what the input password was from the signature of the hash. Okay. So as you can see, this is, okay, you technically don't need to do this modulo in the code because since your input, output, all these types are anyway 32-bit, whatever overflows and goes beyond 32-bit will anyway get truncated. So that's why the operation looks just like this. C1, C2 you can get from, if you go to linear congruential generator, Wikipedia, you will get the values exactly. So as you can see, this is the basic formula. And I think Knut's thing is the simplest. So multiplier is 166, this thing. And this one is this. So this is your generator output. So if you want me to quickly run this code, I can do that. So let's look at the bitwise representation, bit password. So I'll call this, the password was this. Then I copy it and run the hash function on it. And then I'll output all this will be bitwise. You can back convert it into some letter string, but it won't make any sense because it's completely jumbled up. That's why you usually see hash functions written in a very hexadecimal way, because even if you convert it to string, it will look very weird. So this is the hash. Not sure if this one work because code stuff hates me. Why am I doing it on? Sorry, USG. We usually place headers alphabetically if they're within the same category. These are all C standard libraries, so just. Oh, I'm very sorry. This hash is a. Oh, string is also not defined. Sorry. Small code, so many includes. Anything else we want? It said hash. So okay, hash itself as a name is taken by some internal things. I'll just call it my hash. Okay. I'm not using std, so I don't know why it's conflicting. Oh, size. Sorry. Yeah. I have to give the size also. So that is the size of uint.
So Amadip, I think there is a semicolon missed.
Yeah.
That
Thanks.
copy.
Nice. Let's run crypto. Password. Huh, interesting. Why does it say 0? What is the representation of AB? Okay. I initialized it and printed it. What a jackass. I want to say something? I have to print it after I mem copy, otherwise what's the point? So, yeah. Okay, this is not such a very good example because the first number is close to that, but okay, fine. Let's try just to show you that it usually is not the case. I'll just change the thing a bit. Let's make it AA. If you change it a little bit, it should change a lot. That's the idea of a good hash function. That's better. So the representation is close by because you just changed the letters. So in the actual your original text password, it should be close by, but the hash function should change sort of drastically. Okay. So fine, take it. So this is how hash functions work. So basically, when you type in your password, into suppose Google or Facebook, they will take only the hash output from your browser and then store only the hash output. Next time when you type in your password, they are going to generate the hash function again and compare with their stored hash whether your hash is matching. They don't know your password actually. Okay, so that's why they always ask you to reset your password. They can't send you a new password when you request for a password change. Okay, it means you change your password, then your browser will generate the hash function, and that hash function will be sent to us. We won't know your password and so on. So this is how.
So many, but this hash. The hash function you're sending. Okay. Not
no, the hash I'm sending.
The hash, right? So
Yeah.
because the hash is the same as it's the same as the password. No, if you know the hash, you know the password.
Exactly. Now the thing is, these are, if you use a 512-bit, a very good question. This is the basics of cracking like password. The whole area of cryptography is based on this. The hash, if it is large enough, I am using 32-bit hash. So the largest number will be something like this, maximum 2 billion value-wise. If I instead use a military-grade cipher, which uses 512 bits or 1024 bits that are used nowadays by all the standard military installations, it will be so large. These hash functions are usually created in such a way, they're one-way functions in the sense that if I know the number, it is very difficult for me to back calculate. This is not hash. This is not a cryptographic grade hash function. This one.
Okay.
Cryptographic grade hash functions are so complex, you can't find the inverse mapping of that. Okay. So even if I know the input, it's very difficult for me to guess what the output would be.
Right.
So the only way you see, for example, NSA and all these people, they have huge clusters, on the size of what Google has and so on. So what they will do is, suppose this was my input password. I don't know this. but I know that they are using a certain hash function because the hash function is public. It means Google's hash function. They will be on their website also, and so on. Because if you don't even know the hash function, how will you generate your hash and give it to them? So,
Right.
right. So the hash function is publicized. Just that, even though it's so public, no one will be able to find the inverse mapping. If you find the inverse mapping, your name will become a legend in the cryptography community. And you write a nice conference paper and win a Fields Medal or something like that. And people have done this. People keep breaking. Every year, the NSA holds a competition where you are challenged to break different currently used ciphers. And so, yeah.
So that Enigma is broken, no? Enigma machine, which
That was from World War. Yeah, that is. Yeah. So now things are a bit more sophisticated. It will require you at least an exascale cluster to break things. How do exascale clusters break passwords? That is the example of compute bound cores I was going to tell you. So you will only have the hash. Now you have to backcalculate and find out passwords. So what you can do is, or why you need exascale cluster is, let's call
You
this
can also give example of bitcoins, right?
Yeah. But
Yeah.
like that is not. It's a gray area in India. And I don't want to get in trouble.
Oh, okay, sure.
So this was the forward way of doing things, like generate hash. Now, if you want to break the hash, so break hash. So what we will do is we'll input a hash function. So generate hash would have taken a password. So give me a std string. These are the actual functions you'll find in your browsers in JavaScript written. break would be there, sorry. Only generate hash would be there. These are the segues which keep extending the class time. If anyone finds it, like if people think it's boring, then leave it. We'll check this out and go back to normal memory bandwidth and heat transfer.
No, man, please.
So you're given a hash.
You cannot leave us here, dude.
You can't?
You cannot leave us here after saying all this.
Oh, this is so sad. This is so sad. I got kicked out because my time got over. 1 hour. Oh God, please tell me I saved that code. Where is the interactive launch?
Oh, this has 1 hour limit. Oh, you have. Okay.
4 hours, fine. 3 hours.
So limit is 4 hours. For
Yes,
this.
limit is 4 hours. Okay, so you can decide based on usage. Currently, I've built as 4 hours. Where was I? Crypto. Please tell me how much is written. Okay. Recover. Where is recover? And out. Okay, so you have a break hash, which will take in a hash and try to output the string password, but then you have to just do a integer to string conversion. Let's not do that. We'll try to get the original, like the bit password itself. Okay. So basically, I'll return the bit password from the hash. How do you do that? There is good cryptographic hash functions are such that this particular function is very difficult to write. Inverse hash function. So the inverse function of hash. Okay. This function doesn't exist in anyone's brain or methodology. If it exists, that hash is broken, it will no longer be, or that hash function is broken, it will no longer be used by any military or high security tasks. Okay. So instead of that, what is the other way of doing things? This is called an inverse problem. What you do is you say, fine, if you won't give it to me like as a mathematical formula, I will try to generate an algorithmic formula out of it. What is the algorithmic formula? Over all possible u in 32 numbers, starting from I equals 0 up to I less than 2 to the power 32. Or if you want the actual representation, it is -1. This is my candidate bit password. Okay. Candidate bit. Okay, let's call it I. So I just wanted to make it explicit, but okay. It will take a huge for loop for this. So And in this for loop, generate auto hash, my hash, like this only, whatever I was doing, the forward one only I'll use. If my hash is equal to hash, return I, which is my bit password. Now, you can see how big this loop is, 2 billion for an unsigned integer. For military grade encryptions, it is at least 1024 bits. 2 to the power 1024, I think, is a decently large number. Let's ask Wolfram because Google has given up. Okay, 2 to the power this thing is 10 to the power 308. Okay, so you can see what kind of a cluster you would need to actually run this thing. Okay, this is a decent example of what is a compute limited code. Because technically the only input data you have is this number, that's it. You're just trying to run this arithmetic floating point function on this number. There is no array of 1 GB data, 2 GB data. It's just one number, 132. It will fit in L1 cache only. Forget about RAM or L3 cache. Okay, it's just going to break like 10 to the power 30, 308 compute cycles. So this is a good example of what a compute limited code is like. So that's why NSA has all these nice clusters. Well, they don't do it this dumb way. They will parallelize it properly across multiple cores, multiple threads. GPUs are really good at this because it's embarrassingly parallel problems. Embarrassingly parallel problems are basically problems where there's no communication between two cores which are doing the distributed task. So I can break this up into, say, this is my total range. So auto total range. I'm not running this code because it won't end. In my laptop, it will take, I don't know, if the sun dies, it will still keep going on. If this is the total range of my possible candidates, embarrassingly, you can parallelize this task using OpenMP. You can try to use OpenMP, will also give up. It will say, what are you trying to do? Trying to generate 10 to the power 308 threads. There are not so many atoms in your Earth. Okay, so this is how you would do it. And since there is no communication or overlap between the operations between two separate threads, there is no need for synchronization and all those between the threads. Whichever thread finds its answer first, it exits the whole code or something.
Samir, one second. What is this? This total range is the total number of.
Basically, your candidate hash functions are all possible 32-bit unsigned integer numbers, right? So that goes from 0 to 2 to the power 32 minus 1.
Okay.
So that comes to, I think, 2 to the power 32 is how much? A billion, 2 billion, or 4 billion or something. Yeah, 4 billion, 4.2 billion. No? Basically, I can write instead of this, I can write 4.2.
Okay.
I'll try
So
all
this
numbers.
So these hash functions are available at the browser level, you said, is it?
Yeah. So if you look at, for example, MD5 hash, it will be there in your browser behind the scenes, the Chrome code and so on. But if you want the algorithm, it's there publicly, like everything. These are non-cryptographic things, but cryptographic algorithms are also well known. Like, so these are the bitwise operations they'll keep doing. So this is the way you write it. Okay. So instead of that small code, you have these many operations going on, blah, 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 blah. But again, the philosophy is the same. You take in an input and output. See, if we have a small 8-bit thing, 2 to the power 8 is small. We can try that. You want to try that? But I don't know. I wouldn't know the combinations for 8-bit. We can put some random number and check it. So, by the way, this is also how you generate random numbers. Because the better the jumbling in the hash function, whatever input you have, actually that's a good point. Random number generator is also a compute limited code example. So the particular algorithm that you have, like this complicated algorithm or this simple algorithm, if your input is almost uncorrelated or doesn't appear much resemblance to the output, that means it's a good enough jumbler. Huh? And if you have good enough jumblers, then basically the way you generate streams of random numbers is, I can use the same thing. So generate 100 random integers. So usually what you will see is people will ask you to give a seed value, or they assume a default seed value of, suppose, 1, 2, 3. The way you do it is, suppose I've been asked to do 100, so I'll allocate uint 30 to 100. Should be same type. That's the reason why I'll show it. Uint 30 to nums. I will store the 100 numbers here. So for int I equals I 100, this is a random number generator. So essentially what you're doing is you're taking in the first value, you're jumbling it and creating a seemingly unclouded integer. And then you're storing it as the first generated random number. Then what you do is you take that same generated integer and feed it as a hash, seed. Then it will create another very unclouded integer and so on. So basically you'll keep recursively generating unclouded numbers if your hash function is jumbling enough. If it was just, instead of this weird thing, if it was just, so these particular constants and numbers, it takes a lot of time to figure out what the mathematics behind it is and so on. So that's if it was something like this, it's not a random number generator. It's like a, what do you call it? Nothing, scalar. This is the triad operation that we keep doing. Okay. So this is how random number generators, cryptography, and hash functions fundamentally work. Obviously, it's not that simple. There are a lot of layers and things like that. These are the examples of compute limited code. If you're using random number generators and not as simple as this, but you're using something called Mersenne twisters. So again, depending on the jumbly nature of the hash generator, you have different random number generators. This industry standard for generating good random numbers is the Mersenne twister random number generator by this Japanese duo. It also has a very nice algorithm, which looks similar but like this. Okay. A lot of bitwise shifts here and there going on. So what is this? Okay, so cryptography cipher also apparently uses this random number generator internally and so on. So this is a very close-knit group of community of research, cryptography, random number generators, and hash functions. So if you're using random number generators in your scientific simulation, there's a possibility your code might become compute bound instead of memory bound, but you have to just do an analytical calculation and check whether that is so. If you don't like analytical calculations, doing it by your own hand, then use ViewTune, because it will emulate the instructions and try to figure out how many floating point operations your code is using, how many data transfers it's using, and it'll give you something called a roofline model. A roofline model basically gives you a visual representation of which part of your code is compute bound and which is memory bandwidth bound and so on. Okay, it looks like this. So there is a straight number line which keeps going up. Okay, and flops per byte and so on. It's just a weird representation. Fundamental thing is, the question is your code memory bound or compute bound? By memory bound, they mean memory bandwidth bound, not size. Technically, memory bound means you don't have enough memory in your RAM to fit in the problem size. But people keep using memory bound as memory bandwidth bound also. So just be sure what. Fibonacci series generation is also a compute bound operation because it's only one number and you're trying to recursively generate the multiply with other previous recursive function outputs and so on. Okay. So anyway, these are all basics of coding, like theoretical estimates. Let's get back to our stuff because again, the 4 hour will get over and I'll be kicked out again. So this was crypto. I'll just remove crypto for now. Or should I commit this code also? What did I
Yeah,
do?
do that. Comment.
Comment, huh? What happened here? Wait. Why is it saying it's? Oh. Mhm. Yeah. I thought I deleted the subfile when I recovered it, but okay. Okay. Fine. So we'll just comment this code also. We'll just copy paste it. Server has that problem. Become internal to the nodes. Fine. Okay. We'll get out and do SCP. Why did I get out? Fine. Let's get back to our original thing. Benchmarks, SCP. So let's get back to our copy. It's huge.
Is there any other tool apart from VTune, like for NVIDIA GPUs or?
Yeah, Insight. So NVIDIA Insight is the one which does profiling on GPUs. And for AMD, there is AMD's, I haven't looked at, Insight looks like this. It's a horror, but if you're used to, see, the thing is this, if you once understand how to do theoretical calculations yourself, and do it for 2-3 problems, then using these tools will become very easy, because if I told you, okay, you know how to do it by hand, can you write a code which does this? Then you will basically end up creating a software like this only. So they're making it easy for people who don't know how to do theoretical calculations themselves. But as solid programmers, I think everyone, like if you want to be a solid programmer in HPC, it's always good to know what is going on under the hood. Otherwise it'll look like black magic kind of thing. I don't know what is going on. And so like what happened yesterday with me with the scaling, I don't know what is going on. Then I gave up. Today morning, and with a calm head, if you do theoretical calculations step by step, everything will fall into place. Because all this is physics, like electrons are moving around in a particular way. Nothing is random. Okay. So
Theoretically, how do we figure out if it's computation bound or?
Yeah. So basically, that is what I was coming to here only. So see, you will have to look at each of your most performance critical kernels. You have to count the number of plus minus multiplication divisions. Okay. And you have to calculate how many of these equal to businesses are there. Equal to business basically means data transfer. Okay. If it is okay, well, you can have in cache like A equal to B also. That's not much of a data transfer. Just find out how many equal tos are transferring data from RAM back to RAM. Okay. Or from RAM to register to RAM, and so on. So that will give you the data traffic on the memory bus between RAM and processor versus how many compute operations are going on in the processor, in the CPU or the cores. So that will tell you how much the wall time, and if you do the calculations using the core frequency, base frequency for the processor, for the compute part, and the RAM MTS and number of memory channels and all those. So okay, the equivalent mappings are this. Whatever is the MTS or the clock speed of the RAM, that determines the rate at which data is being transferred on the memory bus. Whatever is the clock speed of the processor here, that determines how many arithmetic numbers are getting processed in 1 second. Similarly, for parallelization on processor, parallelizing compute bound parts, you have number of cores, multi-core processors. So you have 40 here. Threads, leave it. There's Intel's hyper-threading thing. There's complete marketing jargon. No need for using hyper-threads. 40 cores, hardware cores. Similarly, for memory bandwidth bound parts, you have number of memory channels. So you can basically, if it's a memory bound code, you will, or memory bandwidth bound code, you will be able to parallelize it up to 8 times in that socket. Or if your motherboard has 2 such processors, you'll have 16 memory channels. So you'll be able to speed up things 16 times maximum if it's a memory bound code. If it was a compute bound code, you will be able to parallelize 40x if you have a single processor, or 80x if you have 2 processors. Okay. So this is it. This is basically all of parallelization here. The second level of parallelization comes from MPI, which is across nodes itself. Like you now have not one machine with 2 processors, but 100 machines with 2 processors. How do you do that? We'll come to that. And once we are done with that, I think everything about parallelization is done. There is no other philosophy. Well, there is distributed computing, but that requires mixed machine coding. MPI won't usually be helpful there. You have to do socket programming for that. So fine, numbers for all scientific purposes, or scientific computing purposes, or engineering computing simulation purposes. These are the hierarchies. Compute bound, memory bandwidth bound, memory bound, which is basically your problem size is so big you don't have enough RAM to fit it in. That is usually not the problem, because before you buy a cluster or rent a node on a cloud service, you should estimate the size your problem should take. And there are two other things which we will come to when we do MPI. One is MPI interconnect bound, which is usually not the case for structured codes. If you're doing matrix transpose operations or Fourier transforms and things like that, then you will go into interconnect bound itself, because there's a lot of data being transferred across your machines themselves using Ethernet or InfiniBand or one of those pipe or wires. And the fourth one is IO bound, which is like you are not doing so much of in-memory processing, but you're reading, writing too many files. So your hard drive speed becomes a limitation. Okay, so these are the 5 categories of bottlenecks you'll have in your computation. Whatever wall time you're seeing basically boils down to one of these or multiple of these types becoming the bottleneck. If nothing was a bottleneck, you will have infinite speed or 0 wall time. Okay, so just remember whatever wall time. Obviously, if your code is properly optimized, if you're not using O3 and all those, if I'm just using minus O0, I don't know what bound it will be. It will be developer bound. Okay, or compiler bound, basically. So, okay, we'll get back to and finish OpenMP.
Samir, there was one thing. So when we are compiling the code, actually we are not using the O3, but for the library you might have shipped with O3, right?
Okay. So you're talking about CMake, right?
Yeah.
Yeah. When you're doing
by default.
Yes. By default, CMake. Okay, maybe I should. I'll come to that. Just remind me when we finish this OpenMP.
Yeah, sure.
Because so basically by default, CMake builds with minus O3 or release version.
Oh, okay.
If you don't specify the build type, it will build. I think that is the case at least till last time I saw. CMake default build type. See, only people are searching for that. No useful answer here. Okay, 2017, what did it do? Anyway, so basically the default build type is release.
Okay.
Why did it not write it properly anyway? Oh, no. Anyway, default build is release. You have to explicitly say debug or rel, these things. Rel with info or debug or minimum size release to make it anything else.
Okay.
Okay, no one gives a straight answer for this topic. Oh, by the way, Google has dark theme now, huh? Nice. Worse. So, okay. Yeah, we'll come back to OpenMP. And so we were doing with 2 threads and we saw it was parallelizing well. We are getting the expected number with 2 threads. Now we want to quickly use the entire memory bandwidth that the whole node can afford. So this node, as you saw previously, has 2 processors. Each processor has 8 memory channels. So total of 16 memory channels. So we should get around 16 into 3.2 GTS into 8 bytes, which is, I think, around 410. But if you run stream bandwidth, so let's quickly write down the calculation, because I am guessing you would, when you're using a node, you would want to use it fully. You have to, otherwise you're charged accordingly for the full node only. For Dutra, if you use AWS, they'll charge you by the core or thread actually. Yeah. We will do a full node estimates. This will be, so the first is hardware estimate. So 16 memory channels, 3200 GTS per DIMM, and we have, so the bandwidth should be 16 into 3.2 GTS into 8 bytes, which is around, I think, 409 or 10 or something, 410, let's say. Okay, Gbps. This is hardware estimate for all the thing. Now we'll do a copy function estimate using, let's do a stream estimate first. Using GCC. So we'll do is, where is stream? Stream is there. Oh, I'm outside. So can we do a GCC? So 3, no, won't let me do. Okay. And I'll go back quickly somewhere. Oh, it forgot my, oh god. Okay. And we'll do it normally only. -03 minus f of an MP string C and p matter. Use 1 billion array size. 1, 2, 3, 1, 2, 3, 1, 2, 3 minus d n times is 10. Anything else? Oh, yes. Nice. It's medium or large. Basically, if you do large or medium, no, it will increase the size of your executable because it will allocate that much of stack. When it is on RAM, not in general. Actually, it might, I don't know. So anyway, we'll run this. So we will use, let's use first of all threads. Actually, this is a good time to show you scaling properly. Let's do it properly then. So we'll export one thread and we will try to see how much we are getting. And then we'll note down here a table of things. You can format it as a nicer table, but for now I'll just write as a CSV file so that you can plot later. So this would be threads, and this would be the bandwidth we are getting from stream. We will take copy as the example. We can take the other kernels also. Usually people take triad, but since we are doing copy, simplest one, let's do copy. So with one thread, how much do you get? By the way, what was the compilation name? -o stream. One thread, total of 7. Oh, 8 GB, correct. 1 billion arrays into 8 would be, it says GIB, which basically is the, so, okay, there are two things. GB usually means 1000 MB. GIB basically means 1024 MIB, where 1024 is the exact 2 to the power 10 number. Since it is close to each other to 1000 and 1024, people keep converting them. But this is a technical difference between GIB and GB, or MIB and MB. The I means integer calculations. So 2 to the power 10, 2 to the power 12, and so on. Versus 10 to the power 2 and things like that. We got 33. Thing will be, so let's quickly keep running for multiple cases. It's a bit big, that's why it's taking a little bit of time. So each iteration takes around, okay, so it came to 43. It's not scaling linearly, which tells us there might be a small issue somewhere. Let's quickly go to the largest one. the total number of cores that are there are 128 total, because there are 2 processors each with 64 cores. But as we learned, these are memory bound codes. So the largest we can use, okay, let's do 128. Let's see what happens. Let's see how much it scales to. Okay, it gives 167. Your hardware estimate was 410 Gbps, which is not even half of that. It's sad. Okay, that means there is some problem. There is a problem. This is not what Stream gives usually. So clearly there is a problem. What is the problem? There can be multiple problems. One is we don't know where these threads are getting generated. Again, if we look at the diagram of our motherboard, it might be possible, okay, when we are using all the threads, it might be that they're getting distributed, but it's also possible that the OS is so bad or so confused that it is spawning multiple threads on the same core, then it is getting serialized on that. So essentially, you have to explicitly tell the processor that, look, I want 1 thread per core only, because I'm generating exactly 128 threads. So please do that allocation properly. No double occupancy in any core, because that is useless to me. So to do that, you should say OMP proc bind. OMP places is cores, and export OMP proc bind is true. Okay, let's then check with the same thing and see if the performance increases a bit. If you're not very sure as to what these numbers or what these options mean, you can again use that tool that I was using yesterday, the MPI OpenMP proc map. Or we can use it once more here to just see what these options do to each of the OpenMP threads and the later on MPI processes also, how they get bound to which core and so on. So it gives me 313 for 128. So I'll just note that down. So okay, fine. Let me record it so you can see later. So this is the number that I'm getting if I do this properly with these things. So we'll continue to use these exports because they seem to be properly instructing or controlling the thread placements. See, you know what? Just as a sample, I'll anyway show you how it looks like. So systems, you can download the systems repo from our repository here and go into MPI proc OpenMP thing. This is an MPI based code, so just do a model load mpich. Because although you won't need it right now for this OpenMP example, it's the code requires it. And then we will compile it. The compilation is usually in the submit script. So just use that to compile. And the run commands. So you can set all these options the way you want, just to visualize how it is going. Okay. So here what I'll do is I'll say, just to run the code, you run it like this. MPI run. We'll come to MPI run, what that means later on. But actually, forget about MPI, just run it, because anyway, that will create one MPI process only. We used how many threads? We did an export of 128. And we used OMP proc bind true, and we used OMP places cores. So you expect each of the thread IDs to serially go on. Thread ID 0 should go on core ID 0. Thread ID 1 should go on core ID 1, and so on. So you can just run proc num, whatever the mpich that name is. Let's see. Okay. So forget about this first thing. So basically, you'll see this string of numbers. Let's just verify that this. So this first slot basically represents the first core, and the number represents which thread ID is there. So as you can see, the first slot has thread ID 0. GTID means global thread ID. What is global thread ID, local thread ID rank? We'll come to that later when we do MPI. So it's correct only, looks correct. So you're getting 313 Gbps, okay, with stream, with this proper placement of things. Now, as we discussed, just as a verification, compute bound codes benefit by parallelization across cores. So if you have 100 cores, you can make your code and compute bound code 100 times faster by parallelizing across 100 cores. Memory bound cores don't benefit that much from core parallelization as such. It benefits from memory channels. So now if I have memory channels which are 16 in number like this, technically from the 1 core case to the 16 thread case, we should be able to maximally parallelize 16 times only the memory bound portions of our code. So should we do that once? What we'll do is we will try to see whether we can get this 300 and we'll try to see where does this 313 number saturate actually. Does it saturate at 16 itself, or does it saturate at 32, 64 and so on? Where does it saturate? So we'll go back to our stream benchmark. So basically this will tell you whether you want to use all the 128 threads or will just using 16 threads be enough for you. If you use just 16 threads, you'll be saving a lot of energy because 120 threads will run on 128 cores. If all the cores are active, you'll draw the full power of the system, which is around 700 watts per node. And since we have 256 nodes, that's quite a few kilowatts. If you're environment friendly, you will not waste that much power. If 16 threads give you the same performance, use 16 threads, not 128 unnecessarily.
But
Okay.
we have to run codes to study the environment.
You have to run codes to study the environment.
No,
Oh, okay.
I'm just saying, like you're using CFD to study the environment.
Yeah, that's like what to say, sad state. Okay,
So in
so
that case, why do you even have 120? I mean, you could have saved money like that.
so that's a very good question. This was actually a good debate we had during architecting the cluster. So the hope was that in future our collision kernels will become so sophisticated they might become compute bound.
Oh, okay.
Okay. See, anyway, right now Entropic might be. It looks like it's compute, but it's not technically. So
Okay.
there was a discussion that was. I mean, plus CFD is not the only workload that this cluster was built for.
Acha, okay.
See, if suppose we leave it.
Sorry, if suppose.
No. This reason, I don't know to get into trouble. No, like there's a reason why we gave this example. So
On your side, disturb.
yeah, no, I was saying there's a reason I gave this example.
Okay. Okay. Fine. Oh, I know. Now I know the background. Little bit.
So okay, let's do stream. So what we will do is we will try to just quickly go over this with these settings. What were the settings we used? We used places, proc bind, true. Let's just quickly see inside this mpitch only. Once if we reduce or change the number of threads, where exactly does it map onto? That way it will tell us whether we are mapping onto. See, ideally, what is the mapping we want? We want one thread for each memory channel. So we'll pin the thread, one thread here, one thread here, one thread here, like this. So after every 8 cores, we should have one thread. So to get that, let's find out what are the settings and export environment variables that we want to use. So we will go to our export OMP places, that whole business. Ports is fine. We'll pin to ports, that is okay. And then what we'll do is there's a simple enough, instead of explicitly telling, okay, 0, 1, 2 like this, what we can do is we can just tell that you spread it. Okay. Spreading basically will take the entirety of the range of the thread IDs and then uniformly spread them at regular intervals, which basically serves our purpose. And then what we'll do is we will export only 16 threads because that is the bandwidth, that is the number of memory channels we have. Okay. Now we'll run this proc map. See, so if you can see the placement here in this, you can see 0 is on core 0, then skip. Then on core 8, which is basically this core, this core, you have thread 1. Then again skip. Again core, what is that? So if you actually count it, you see it's correct only. 16 threads have been nicely placed. So we will use this variable. So You can also see the distribution here, which CPU ID, which thread ID. So thread ID 0 went to CPU 0 or core 0. Thread ID 1 went to core 8 and so on. It's a nice tool you can use to always verify with what, whether you're pinning correctly or not. So now we will use these settings to run stream. So these exports remain the same, will be reused. And if we want to run stream, just to run stream, that's let's see, 16 threads running. It gives us 340, which is much larger than 313.
So with this, I have one question then. Like,
Yeah.
see, I mean, yeah, I think you had already told. See, right now, at least I'm running with 32 or 64 cores per node. So, with, I mean, if I see this example, in that sense, so actually my code will be performing worse than if I had run in with 16 cores, is it?
Yeah. No, I understand your question. The code that you have has multiple different types of kernels. Some are right now memory bound in different ways, and optimizations are being done differently when you compile using. See, right now we are compiling all our codes using one single shot, that CMake build thing.
Yeah.
If you actually analyze each function separately, you might see that each function needs different optimization flags. If you mix all the flags together for all the functions, some kernels will actually go bad. So for example, if you use Intel compiler, and if you use AVX and streaming stores together, Golide becomes 5 times slower, but advection will still become better. So these are, so ideally for the best optimized case, you have to analyze what all is the best assembly code for your particular functions and then compile them separately into libraries, then link the libraries together. With things. Okay. So we'll do that. We'll do the exercise like separately for each group whenever that. Right now, when I calculated with Chakri, right now the current codes are running, at least in the LB part for Fluid, is running at 2x slower than the theoretical estimates. Okay. So 2x is okay, fine. Okay. Instead of 4 days, it'll take 8 days. It's not going to take 2 months, so it's okay.
So 32 cores is fine, no? Is what you're saying? Or,
which one is fine?
I mean, so what will be the number of cores that I should use per node? So right now I'm using 32.
Right now, just use 16 or 32 because the particular why I'm suggesting this actually comes for a different reason. For certain MPI processes, we'll come to this when we do MPI. For certain MPI processes, we see that if you use all 128 cores per node, there is so much of MPI traffic happening on the same network controller card or InfiniBand card. It clogs up the InfiniBand on the node itself. So then you'll get a lot of delays, accidental delays. You'll suddenly see your MPI is just stuck somewhere.
Yeah.
You don't know why. So that because the thing is, MPI as a thing was developed when AMD did not come with this huge monster number of cores per machine. Okay. So slowly MPI, the implementations will be revised a bit to make this more smooth, but it will take a bit of time. So right now the optimal best, actually it will be using 128 nodes becomes much slower because of MPI bottleneck only for us. This clogging happening. If you use 116 cores, use this smooth, it will go. So whoosh. Like I was doing this benchmark on Ahmedabadi and 128 core, even CAD was not running. And I was like, what is happening? CAD is supposed to run. Then I used 16 cores, within 1 second it finished CAD. I was like, wow, this is the... Especially if you do collective operations. Not for MPS and receive, collective. Like certain operations have gather and broadcast and all those. Those are the ones which will block. So you will see the MPI stalled at one of those broadcast or gather kind of. We will come to that in MPI. We'll finish this. So this is N. So N is whatever. N is 128, 1 to 16, 128, and so on. And this is the thing we are generating from there. So if you do 32 and 64 and things like that, you will see, you will get a rough map. So let's do it. Obviously, this will be half of 16s because you're not using all the channels. So not half, okay, fine, 263. It's not linear also. MD is not that. Well, you can sort of. No, it's not linear actually, yeah. Because there is it depends on the hardware. There's nothing you can do. Means you have asked the AMD why does it happen and so on. They are like, sir, what will we do? Ask the hardware people. 339. 32 starts going down and then it will go down. 64, another number. Okay, so you can see it's going down after 64. So what we'll do is we'll quickly plot it and we'll see the first scaling curve. This kind of problem is called strong scaling, where you have a problem, but you're increasing the number of threads to increase the number of parallelization on the same problem size. We had a problem size of 1 billion elements. So this graph that you're getting with increasing parallelization, what is the bandwidth or what is the wall time that you take? So you should technically also write the wall time. But okay, so you know this problem size, so dividing by bandwidth, you get the wall time. That's okay. So we will just plot it quickly. And usually when you go to conferences, this is the first graph people want to see. This is strong scaling. As opposed to weak scaling, where you keep the problem size same, but spawn clones of the same problem across multiple threads. Or basically you keep increasing the size with the number of threads and so on over time. Okay. So this is the thing, and if we do no plot, and let's say data file separator, from CSV, but okay. One is to do with line 5.7. We'll see, this is the scaling thing that we got. Just give me 1 minute, I'll just use line width 2, 3. And size 2. Set. That didn't help much, but okay, fine. What you can see is, and since we are increasing in multiples of 2 or powers of 2, we'll set log x. That will show it nicely linearly. Yeah. Okay. So as you can see, it scales very nicely in this range up to 16 cores, and then it starts going down. So okay. Memory bandwidth, limited part. So this roughly tells you that your theoretical model of how a machine works on memory bounded codes, that is correct. If you instead did that crypto problem and parallelized across 128 cores, you would see it is almost going up linearly up to 128, because as many cores you have, compute one problems will scale linearly. Almost. It'll saturate because of machine heating up and slowing down, throttling and so on, but modulo the small deviation that scale linearly. So same thing we'll get for our simple copy example in stream also, hopefully. So we have our code, we'll just change this once. Why is this terminal looking half? I don't know. So we can go back to our simple copy code, and since we are now parallelizing across multiple threads, we will not put this if-else condition. We will write OMP parallel for. So essentially what we would have done is, instead of writing an if-else condition, as we were discussing yesterday, OpenMP allows you to write this as a for loop by itself. Instead of manually breaking up the task, you keep the whole array and let OpenMP break it up for you. So this is the one, this is the one, and you do a OMP for, or if you want to write in one single line, that is also okay. You can write pragma. Similarly, here also, you can remove the manual hard coding of if-else condition. Right. And here you have OMP parallel for. Please remember to move this away, because if you keep this bracket with OMP parallel for, it basically means you're trying to parallelize a bracket only, not a for loop. So yeah, so let's see now. Should we print the elapsed bandwidth also, so that we could quickly see if we are getting the correct time and so on? So you know the elapsed time. So per sample we'll leave it. Total time is this. So we'll do a bandwidth calculation in code itself. So my bandwidth calculation would be double of bandwidth is, what is the data size? So that is nx elements into 8 bytes, or you can do size of double, that will give you 8. Into how many number of iterations you're doing, that is data traffic, so n samples, into number of operations, memory operations that you're doing. So 1 read, 1 write per variable. So 2, 1 read, 1 write. 2 comes from 1 read plus 1 write. So now if this is the bandwidth that we are getting, you know what we'll do? We'll quickly put a bracket here, because integer into size of double, 8 billion will overflow nx, because nx is of size unsigned integer int, which can store only up to 2 point something billion. 8 into 1 billion will become 8, so in the end you'll start getting a negative number. Like this is what happened, is the popular legend about nuclear Gandhi, no? Again, in a game called Civilization, they were coding people's peacefulness versus aggression numbers as a 255, like 255 is basically what, 2 to the power 8, I think. Yeah, 8 is 255. So 8-bit integer, they were storing it as a car. Yeah. So what happened was, when in certain phases of the game, when during 1950s in the game storyline, when nuclear bombs were being made, and apparently Gandhi was also alive, so suddenly everyone's aggression rating went up by some number, but Gandhi's was supposed to go down. And if someone started Gandhi's aggression rating at 0 already, they had hard-coded Gandhi's aggression rating going down by 2. So it became -2. No, so basically it became -2, but unsigned 255-bit integers cannot represent negative numbers, right? So it overflowed back to 254 or 255 or something, 254 basically. And then Gandhi became a very, very aggressive guy who was blasting everyone with nuclear bombs. So this is a legend. Apparently Sid Meier's, who is the creator of Civilization, he said this is a popular legend. I don't know who made it up. There was no bug like this. I make decent coded games. I don't code crap like this. So if you want to know the story better, Civilization, nuclear Gandhi. Okay, you'll see a lot of fun memes and so on. Okay, like yeah. So.
Okay. So even Bitcoin has this limit, no? That this total number that the like your account can be negative and stuff.
Oh, no. So there is one. Your account can be negative meaning the number of the
like the transaction, as in the total number of bitcoins is a constant in some sense.
Oh yeah, right. Well, that basically that is correct. That is true also for stocks also, no? Unless there is explicit. Yeah, it is
correct. Something, yeah. So there is always I mean, that cannot happen. You cannot get negative and stuff, right? Like, so that is already coded in.
It depends on the code.
No, that's what I'm asking. Okay.
But like if they're using unsigned integer something, yes, you can't have negative numbers, but you can have overflows which round back to.
Right. Yeah, that's the.
So if you have numbers which even unsigned integer can't store, you go to unsigned long. If you have numbers which even 64 bits can't store, then you go to 128-bit numbers themselves instead of 128-bit registers. And if you want to do something like that, there's an emulated big number library called the Big Num library. It can store arbitrary position numbers, big num, MPFR, MFR. MPFR. Okay, so you can download this and use numbers like with 1024 bits and things like that. Okay, these are required for prime number factorization and things like that, because people are going crossing large numbers to search for the sequences and so. So, anyway. Okay, so we were trying to calculate the bandwidth. So this is the bandwidth. So what I did here was essentially, okay, this won't help. What I have to do is I have to just convert it to double. So the C++ way of converting a number to some other number is static cast, not just the bracket thing. But you can do the bracket thing because C++ consumes C as a subset, but nice way of doing it. This is better. Okay. So I think this is the bandwidth. No, this is the memory. This is the total traffic. Size is this. these many bytes. If you want GB, in GB, then it's 10 to the minus 9 into this GB. Okay. And you have seconds, total time elapsed. Then your bandwidth is your traffic in GB divided by your total time. This is in Gbps. So you can print total time and bandwidth. So we'll just print bandwidth now. Okay, let's print time also. But later on, when we go into complicated codes, we only have the wall time to look at, not the explicit bandwidth calculation, unless we want to do it. So bandwidth is something in Gbps. BW. So I think we are ready here. We'll quickly compile our code. Settings will keep the same. OMP num threads, OMP export, blah, 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 all those things. Where is this? Oh, no, not this. Where is the other one? Stream. So this is how we had compiled stream. So let's quickly do that and reuse it now. So we're not hard coding these things, so we'll remove this. We'll pass it as dynamic runtime variables. p.cpp, Mac model medium. We don't need this because ours is not a static array. CC, it becomes G++. Right. So, oh yeah, auto is C++ 11. So now, export OMP. We'll do it 16 to see what is the maximum number we are getting. And those are already there with other options, codes, and we'll just do it just to be sure. Okay, so copy 1 billion, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 10. We got 230. Wait, did I make a mistake in our calculation? Proc bind spread. Correct only. What is this? And again, same thing happening. It's going even lower. So the question is why? So basically what we were doing previously is we would have gone to just give me 1 minute. Oh, but I was compiling this thing only, stream also was being compiled by the same GCC. That is fine. No, one is the flags might be a bit different. Okay, let's do that. Let's use a more newer GCC. No, it will be something like that. Like either if it's not GCC, then we'll use ICC. It's okay. That, the only thing is, I think the problem is alignment. Because stream is aligned. But this won't change much. Okay, so what we'll do is we'll quickly try to change compilers and see whether we can reach the same thing. We'll go to Y that is that. Oh, sorry. We'll go to Y that makes sense. See, okay, no, not change compiler. Sorry, that's not the first step. There's a small thing that usually good codes which require parallel processing do. That is, when you are allocating memory like this, let's go to this picture. When you're allocating memory like this in a RAM, usually processors, when they're fetching data from the RAM to the cache or processor and back, writing back, they prefer to not to do it in one as one variable at a time, but they fetch a bunch of variables together. So basically, if you can imagine your RAM, so let's just create a new slide. I'll just roughly show you an outline of how it looks. So if this is your RAM, usually you'll have all these memory address spaces, like suppose this is the first 100 GB of your RAM, and so on. First 100 MB of your RAM, this is second 100 MB and third 100 MB and so on. You can imagine these partitions like this, and a lot of data is stored, like 100 MB worth of data is stored here and so on. Inside this, if you zoom in, it will be smaller chunks of 100 KB, 100 KB and so on. Usually RAM data space is partitioned into bunches of 64 bytes. 64 bytes means 512 bits. Okay, usually, it depends. It's called a cache line. What a cache line basically means is that if you had this core to which this RAM is connected, when you're going for some kind of data fetching from one bunch to this thing, to this core, the data will be fetched in bunches of 64 bytes or suppose 128 bytes and so on. So how many bytes are being fetched in a group, in a bunch, is called a cache line. It is being fetched from the RAM to the cache of that processor. Okay. So now suppose you allocated your data and your array, this A array, happened to straddle two cache lines. So suppose these were the cache lines, and this is my entire AX array, like this. If suppose if my array started like this, then the processor, this is an optimization that is done at the hardware level. There's nothing much you can do about it. This is how the processors are made nowadays. If the processor wants to access the first element, it will go to the lower bound cache line and take in all the data in this bunch itself. Okay. So it will take all the data that resides in this small cache line block. Okay. And then if you want to access some data here, it will pick up the entire block of data here. Okay, like this, it picks up blocks. It's called cache line. So if you really want a better diagram, I think a better diagram you can find here in the online of this. Actually, no, this is not the correct one. Cache lines only. Let's see. Okay, fine. Really difficult to find diagrams exactly like this. So, by the way, OLSSS is something a bit different. I was just trying to use the diagram, not make the two concepts same. Okay, so this is the cache line concept. So basically, instead of one variable, it will try to get a bunch of variables. What is the bunch size? That depends on the processor. So, for example, for AMD, as far as I remember, it is 12 into 32 bits. How much is that? Or something like that. It'll either 16 into 32 or 10 into 32 bits. Some weird number it will be. Okay. So essentially, the idea is you need to, if you want this kind of misses not to happen. See, by misses, what I mean is, if I was trying to access this first element, it will try to bring in all these surrounding elements also. It won't use them per se, but that amount of data will be transferred as a backup, like as a side effect from your RAM to cache. So that whole cache line of data is anyway going to take up your memory bandwidth. So why not make sure that whatever data is being transferred from RAM to cache is the data which you actually need, not backward data. Okay. So the way you do it is, instead of starting your arrays or allocations from in the middle of cache line, you align it with the cache line. That way, if it takes up, if you want to allocate, bring in data from here, it will pick up a bunch of data from this array itself, so that in the next for loop, when you needed the next data in the for loop, it will already be present in the cache. So it doesn't have to transfer it back from the RAM to cache again. This basically, so if you align your data allocations to cache lines, you will be not doing cache misses. Okay, or basically transferring useless data to the cache and clogging up your memory bandwidth and things like that. Okay, so to do it in C++, one way to do it, this might not be the reason of getting low bandwidth here, but I'll just do it anyway. So because stream bandwidth internally does it. Okay, or we can just quickly use stream bandwidth to verify the stream style of doing to verify. So it will do something like, where is it? POSIX, sorry. So here it uses static arrays, but if you go to the MPI version of stream bandwidth, it will use something called a POSIX align. So let's quickly use that once. Huh? So where is the thing? POSIX mem-align it will use. Copy this. So this is one way of doing it. In C++20, I think there is a keyword called align which is coming up, but unfortunately we don't have C++20 compilers. So instead of doing allocation like this, we will use malloc. When you use malloc, this equivalently becomes malloc. Next is the number of elements into you give your size of. So this element size is double. Sorry, comma, I think. And this is what, comma or into. Single word. So into. Basically, malloc argument is how many bytes of memory you want to allocate. And you say it's a double type pointer to generate like this. Or I can do static first. Actually, you do use a C syntax because malloc is C. If you're using C, then cstdlib is there. Okay. Huh? So this is how you generate, use malloc, but this is not aligned malloc. Huh? So some compilers give you a malloc and things like that. I think CUDA does something like that, or DPC++ does. But simple C compilers don't have any fancy functions like that. So you have to write your own fancy function to align it. How do you align it? You give the array bytes, which is basically array elements into size of double. So let's double. So basically, instead of writing this, the aligned way of doing it is, okay, we'll just do exactly how it works. Yes, this is the pointer where the aligned array will be generated. Okay, this K is nothing. K is basically a error flag and so on. So you do it like this. Array alignment, you give a number of bytes. So we will say 64 bytes, which is 512 bits. And array bytes, which is basically the number of bytes you want to allocate, which is nx into size of double. So when you're going to use your array for long operations, no, it's a good idea to use something like this. Internally, if you're going to use SSLabs code, which we'll come to we'll come to in the next half, all arrays are internally aligned to 4096 bits, which is I think something bytes, which is good enough for any future machines also. So if you're using SSLabs core arrays, you don't have to worry about those. Arrays means, I mean, those blocks and all. So those are internally aligned. So that's not an issue. But if you're writing your own code, just remember to do this. And since we have done malloc and not new, we won't use delete. We will use free.
Something just general question. This is it better to use calloc than malloc because that
you can see. Okay. See, the thing is this: if you are using calloc like this, no, you won't get the option to initialize close to the RAM that you want because it will initialize with 0, allocate and initialize with 0 at the same time.
Okay, got it. Okay, that allocation is not it's not aligned.
It's not respective to the thread distribution that we use.
This has to be done manually, basically. Okay.
It will be better if you do it. So this will be. So this is how you align alloc or malloc. Align malloc. The only other small thing is for this function to come in. This is not a standard C++ function. It gets triggered only when you include something pragma like this. So I just do that. Don't ask me why. It goes into how GCC is written. Not just GCC, like any compiler. So yeah, we'll try with this once and see if we are doing any better. If not, then we'll change compilers and try to see if we're getting better results elsewhere. because GCC, as we know, doesn't have a particular automatic, it doesn't generate the best assembly, because Intel people and AMD people know what is best for their proprietary hardware that the open source GCC community doesn't know. So let's first do this. So then you'll ask them, how did Stream give the best result? So Stream is using with OpenMP static and a bit different. That should make a difference. This should give the great result also.
So open source community does not know. I mean, like that internal
There's
structure is
some-
that kind of
Yes.
secret.
Yeah. There are some optimizations that are still not in GCC, which are there in Intel and AMD compilers. Yeah.
Okay,
You know
so
what? Current AMD and Intel, the newer Intel compilers, which are going to be free, they are basically forks of the LLVM Clang compiler. And they just take that open source compiler and add their proprietary optimizations on top of it and call it Intel and AMD compilers, ICC and AOCC.
And that is what their actual compiler is. This is
Yeah.
not some whatever open like freely they are giving. It's not what is the diluted version of their actual compiler.
No.
Right?
So if the free version that they'll be releasing now, so AMD is releasing free versions since the beginning only. Intel from this year has started releasing Intel compilers for free. And the free version is based on LLVM, not the classic. Initially, till last year, their baseline was a proprietary compiler from scratch. But they basically took down that entire team and asked them everyone to start forking from LLVM because that is how most of the industry is going, because AMD's AOCC is also a fork of Clang. So basically they take the basic Clang code, then basically a lot of features already there in Clang. You don't have to rewrite the same thing, it's just redundant code. Like,
Why
you
did
just
they do that, Intel? Like instead of
I think they want to cut costs. Like instead of having 100 people in the compiler team, they just want 20 people to add on to Clang. It's just redundant code base and so on. But the free compiler that they're releasing based over LLVM, that has all the features. Like that has all the optimizations. We have tried
Okay.
that with all the.
Oh, that's like old Intel compiler only.
Yeah.
Oh.
So
Yeah. So about this Clang thing, so why do many people don't use? I mean, if
no, you
that
can
is
use.
the
That's not an
case,
issue. It's just that Clang came a little later, I think. GCC was older. That's why GCC is more popular. Or GNU as a community. LLVM is more focused on all this compiler and some other tools business. GNU as a community is much larger and encompasses everything from GIMP to this thing, that thing. So yeah, but you can use Clang. Clang is actually nicer.
Okay.
Even Cray's own compiler is based on Clang. Everything is based on Clang nowadays.
Oh.
Yeah, that's CCE. Yeah. Okay, this is not change, but it's a good idea to usually this thing line your things. There would have been a better example I could have shown where this actually makes a difference. Actually, it will make a difference in your SMD codes. That there you can't get away with misaligned. Means you can, but it won't give you performance. So there's something else happening here, which we'll try to figure out. Am I doing something weird? Let's see. As a last ditch attempt, what I'll do is I'll just make it exactly like Stream, which is I'll make it static array. And this we won't need then. The only other thing is we'll do a reference value print, because then the compiler might think you're not reusing any of this stuff. Maybe I'll just generate some. Oh, okay, yeah, that is why it's happening. Yeah, this compiler is trying to be over smart and shooting itself in the foot. Oh, sorry, type. So that is another thing which you get across only during benchmarking. Now we'll have to use that Mac model. Oh, what happened? Okay. Yeah, this exposes the problem. You see what happened here? Even though I give a 1 billion size, it finished in 10 to the power minus 5 seconds, giving a million Gbps. What it basically means is that the compiler was trying to act smart and generate an instruction which basically assumes that since I'm not printing, I'm not going to reuse the value. So I'll just try to do some optimization here. In this case, GCC was trying to optimize in a weird way and was not getting away with it, like it was screwing up the speed and so on. So what we'll do is we will just try to print a reference value. So as a reference value, I'll print the 100th. 100.
Somebody put volatile worksheet.
But it also works, but you want to use volatile.
I'm just wondering.
It will work, but the problem is, in C++, volatile is a very weird thing because there the volatile basically, I am not very sure what kind of assembly volatile we generate.
Oh.
Basically, compilers, when they see volatile, they give up. They say, I am not going to touch this guy. So it won't try to optimize that part. Okay. So I usually don't use volatile unless there's an object-oriented reason of doing it inside a class member and all those things. It's where you're not very concerned with performance. There are places in performance-bound codes also where you use volatile, but that is only for atomic operations. Like, whatever, anyway, leave the atomics. It's complicated stuff. See? Beautiful. The moment you put that reference value, and GCC said, Acha, you're actually trying to verify the values, is it? Now I will generate proper code. Okay. So this is, I think, a very long drawn road to a simple lesson is that when benchmarking, just remember compilers try to be smart, they're not very smart. They just try. So just tell them explicitly what you want. That don't try to optimize this away and end up screwing yourself. Because basically it was trying to optimize this away, but OMP, when it is there, it is not able to optimize it fully away because it doesn't actually know how much of other complications are there inside this OMP pragma itself. So it was in the middle making some khichdi out of it. And so then when you said, don't optimize this away, I need the value of AX later on. So when I printed a sample value, then only generated the actual code, which is 341.83. So yesterday also this might have been happening. The random timings we are getting is basically the compiler trying to basically generate random assembly. This would have been a good time to generate the actual assembly of the code without the print and with the print and see what is the difference in the code. That would have given it right away. But since you saw how horrible the assembly codes usually look, that's not the first thing people go to. Okay. So for stream for copy function also, we finally found that we are getting this. I want to say that. Or you want to remind me that it's break time now, huh? I know. So fine, we'll do the MPA after the break. I know it's taking a lot of time, but I think these are good lessons to learn. Oh, by the way, if you just want to verify that this is not because of static double, we did that, no? We ran without static double also and got, that random thing. So we will run without static double. We'll get back to, we'll comment it out. We'll get back to our original code.
So why are we not using AMD compilers then? Because
we can. I'm just using GCC because everyone likes GCC. You want to use AMD?
Yeah, I had the same question too.
Yeah, fine. We should get the same number from all of the three. That's the idea.
Oh, is it? Okay. Oh, that's...
We should. Yeah. Oh, if you really want to see, Ravi has done a proper study, I think. There is a... actually, that repo is not public because it's under NDA. Because we keep having these collaborations with these people, AMD and Intel, and they put NDA. So even for Santosh's talks, they have refused to give the new Ice Lake numbers, allow us to talk about the Ice Lake numbers because it's under NDA. Because, this will not sound very nice, but the current sad state of situations is AMD is beating Intel hands down so badly, Intel doesn't want anyone to show in conferences what their numbers are compared to AMD. Okay. And there's the same reason why we have an AMD cluster, not an Intel cluster. Oh, no, not this one. Sorry. Wait, I'll just quickly show you where.
Blur it out when you upload the video.
This one. Oh, acha. No, that's fine. This is within the company, so okay. I'm allowed to.
But
If
you
you
put
want,
the
we can
video on
actually
YouTube, right?
access. Uh-huh. Oh,
You put the video on YouTube,
but
right?
it's unlisted. Oh,
Okay.
oh, acha, I see. It's a gray area. Understood. So we have this thing. We have back and forth these things with them, where we verify that. Hey, Ravi, where is the where is the comparison between ports? Okay. Stream performance on Ice Lake ICC versus GCC or Skylake. Okay, Skylake. So, for example, the Velankini nodes that we had, you can see that. Just a comparative table, is it? Okay. So, as you can see, with CC, which is Cray compiler, we have 200 around Gbps on Skylake. Then with which one? GCC. GCC we have 175 because on previous generations of Intel processors with Skylake required a particular operation called streaming stores, which was not there in GCC. That was proprietary to Intel and AMD also. So since it was not there in GCC, whereas Intel and AMD gives 200 Gbps, GCC was able to only manage 150 around that. So those we know on. Actually, for the same reason, if you have noticed, in stream also, when we were running it on Rudra, copy was giving correct things. Okay, 340 and so on. The other ones were still at 200. Did you notice that? If you go back in the video, you'll notice this. That is the reason why that is happening, because GCC is not able to optimize the triad and the add and the scale operations. For that, we'll shift to AOCC or ICC. Okay. We are currently shifting to ICC mostly, not using AOCC, because AOCC has some bugs in it, and we are constantly hammering the AMD people to fix it. So this is the one. So 3.00 actually contains some of the changes we requested from them. Yeah, this is basically the verification that it actually works. So anyway, so basically AOCC is still under iterations with us. Once we ensure that we have all the required optimizations inside AOCC, then we'll start using AOCC. That will take a bit of time, at least 6 months more it will take for it to be stabilized. Okay. So, okay, we'll quickly get back to our this thing. Previous code, where we were using simple stuff, not all this fancy align and all this. Just show that might not matter. In this case, the line might not matter that much. It will in some cases. Align is not a bakwas thing. It is actually a very useful thing. In this case, we can do away with it. So we'll keep it the simple old code that we had. NX, everything is fine. And we'll get the run. How many threads are you launching? Okay. See, I think that was the difference. So let's do the align one thing. Or is it static one? I don't know which one. Any one of those. Basically, it's basically GCC's thing. It's not a usual problem or a common problem. Just get this done and then we will break. Let's get the copy kernel to the correct value, then we are done with OpenMP parallelization. And we'll go into MPA. This one, we require this. Dynamic array. And if this also doesn't work, then we'll shift to ICC or something. Okay, this doesn't work, so we'll shift to ICC. It's not working because GCC basically is saying that I need the length of the array to do my optimizations. I can't do it with dynamic arrays, even if you align it and so on. So let's then do it with ICC. So ICC will be module load ICC. Ravi, we never tried MPI stream with GCC, is it? Or it gave the low results? Huh? Interesting. Okay. If you run MPI stream, which has dynamic array with GCC, I think that will give the low results. You can check that also, but it doesn't have OpenMP. That's the problem. I have to do it separately then. So let's quickly do it ICC. See whether it's able to generate the correct code. CPC minus f OpenMP. If this also doesn't generate, then we will put in a flag which will help generate it. Because this we have verified. So, okay, this is a good lesson of how the open source community has been crushed under the corporate boot of capitalist overlords, if anyone is into that kind of thing.
Nicely put.
Yeah, man. Now it's recorded, so believe me.
But
Now, Reliance people will come after you. You know?
That is like 100 Gbps more, man. It's like insane.
yeah, okay. So as we can see then, we will just note this down that this one gives bad, GCC bad. That's why I wrote GCC. That's why I was saying, keep a note of the compiler versions because that will screw things up. This, just ignore the and here we have this thing. Now the question is for what threads? I have to just quickly check. Did we do 16 or 128? This was with, so let's do echo OMP num threads. It will tell us how it is set to 16. Nice. So for export OMP num threads. I've been kicked out again? No. So this is the sad situation which we have. So that's why we will try to use Intel compilers mostly. Whenever AMD compiler gets stabilized, we'll again do a thought benchmarking of the new versions and then we'll let you know. But for practical, see, the reason why we're not usually using ICC is because till now ICC was licensed and you had to pay 2 lakhs for each compiler. Now that it's becoming free, you can download it. If you want to know how to download Intel compilers on your own machine and try, you can visit systems repo. And there is a issue called installing OneAPI. OneAPI is basically the whole suite of Intel products that Intel is rebranding to. So it has all these things. You can just copy, like follow any of the instructions here. So just these things, that's it. You can locally build and then you can, it shows roughly it will take 1 hour to install the base toolkit and 15 minutes to install the HPC toolkit. Yeah. Actually, you know what, don't do this one. Use the one where we have shown for Belankini nodes. Okay, use this one without user sudo as normal user only, and then you can run ICPC, ICC, Intel MPI, everything for free. Their model has now become that we give you the compiler for free, but you can't complain. If you have to complain, you have to raise ticket on a private customer support forum, which is paid membership. We have free membership of that currently because we are collaborating with them, but they have said the day the collaboration ends, you have to start paying for customer support. Okay, so this is the ICPC business. So I think we are done with MPI, OpenMP for our codes. If you really want to see that all these were not necessary per se, we can even go back to our normal thing. So basically it was this open source versus proprietary all along. You can go to the unaligned thing also and check if it gives. It will give, means it will give the high numbers only, because in this particular problem, alignment will not be that much of a difference, make that much of a difference. And we don't need to do this Mac model large because we're using dynamic arrays. Okay. So we can just write a simple code. We'll make it simple, huh? Because anyway, the actual alignment and all those instructions you don't need if you're using code libraries. If you're really interested in writing your own libraries, you can always see the instructions in this video screen. That way you'll have to watch the video. And please, whoever is watching the video and liking the video, please give a like and subscribe to the channel.
Press the bell icon.
No sharing. We can't share.
You're sharing with? No, you can't share. Yeah, it's proprietary.
Like,
Confidential and proprietary. Yeah. Oh no, see, the problem is you can't, there's no point in clicking the bell icon because these are unlisted videos. So it won't. Because if I make it public, then I'll get so much hate comment from certain community of developers. See, GCC people will start hating on this video now. So, okay, so we'll make it simple enough. And we will just verify again. Always verify. Just to see the scaling, 16 gave this. What does 128 give for I6C? Does it saturate? Does it give even better than 342? 316, lower. 64, let's see. Should be a bit better than 128, but not as good as 16. Bit better, not as good. 32 will be almost as good as 16 because so 42 what is statistical fluctuation. 8 should give not half exactly, but close to half. 4, oh, sorry, not here. Again, I'm just changing the number of threads because I've already set the other environment variables to core. OMP places core and OMP proc bin spread. This basically ensures that whatever number of threads I'm using, they're uniformly distributed across the 128 core interval. That is very important. If you want to get all the theoretical performance jargon that we used to explain. 4 will give you this, 131. So as you can see, here to here, beautiful scaling, exactly double. Okay, 4 to 8. And 2 will hopefully be 65, huh? Play fractions, like division actually works in life. 132 by 2 is 65. And this should be 32.5. Right, where's the run? So scaling works. Beautiful. Okay. So this is OpenMP. Finally, coming back to our simple code, we see that we have used OMP parallel over a for loop. Before we go into MPI, I will show you what roughly MPI does, or what are the key points of parallel programming itself in OpenMP, like for example, collective operations like reduction or synchronizing threads and so on. And the same concepts will pull over to MPI, because MPI is nothing but the same kind of parallelization, except instead of parallelizing across cores or threads in the same node, you will be communicating across nodes themselves also. You can use MPI within a node also, but you'll be parallelizing across. It's mainly used for parallelizing across nodes. Like suppose you have a laptop and you have a desktop. How do you make them communicate? If you want to run 2 portions of the problem in these 2 separate machines, that is when you use MPI. You can't use OpenMP there, because OpenMP sees only the code and the memory that is there in your node. It doesn't know what your laptop has, and so on. Okay. But MPI will know. MPI also doesn't know. It just gives you a way to communicate between the 2 machines. If you wanted to really go deeper into communicating between 2 machines, then you have to learn a bit of networking, TCP, UDP, socket programming, and all this. But those are not required. MPI is usually the standard message communication procedure for HPC. So we'll use MPI. Okay, sorry for taking so much extra time. It's almost half an hour again. We'll break at 1 and we'll come back at 2:30. 2:30.
2 is fine.
So
that
okay. Okay. Yeah. So in the meantime, I'll just clean this repo up and commit the changes so that we can start afresh from MPI. Okay.
So Samir, just I had one thought. So this, what you had explained till now, so the processes are clear. It's like you have some data in the RAM, you fetch it, and then do some operations on it.
Yeah.
So, and you also said that it's fetched in like chunks,
Chunks,
the
yes.
cache lines and all
Yeah.
that. So, so can this be interleaved? Because it looks like some parts when they're fetching, you can do some computations and stuff like that.
Oh yes, yes, yes. That the processor will do for you. You
Okay.
don't you
Oh,
can't
okay.
you don't have control over that.
Okay, okay.
That is why Intel makes money, and that is how AMD makes money. That logic there, right?
Right. Okay.
That interleaving, yes, it is very much interleaved. Otherwise, it will be very slow. Yeah.
Correct.
Yeah. So fetching actually basically means pre-fetching. So when the current computation is going on in the core, the memory controller is actually fetching the data which is predicted by the compiler for the next step.
Okay.
So it's called pre-fetching like that. Yeah.
So compilers are very important in this sense.
As I discussed yesterday, compilers are important only if you want them to generate the assembly by default. If you know assembly language, you are the compiler.
No, obviously. Yeah.
Okay. Fine, we'll then come back.